So welcome dear students and hope that you are doing great. So today we will revise the whole chapter solution and the main focus here will be on multiple choice questions, very short answer type questions and short answer type questions which will be asked in the board exams, right? So without wasting your time, let's start. Our question number first is that which concentration term is used to express the concentration of very dilute solution? Now, since it is given that solution is very dilute, dilute means the concentration of solute that is very minute, it is small. Then which concentration term we will use? So you will remember here that the concentration term which we will use, that will be the ppm, parts per million. And you already know it is the parts of one component upon the parts of solution into 10 to the power 6. Just if we take let's say a mass of one of the component, let's say mass of solvent upon the total mass of solution, right, into 10 to the power 6. So this is how we calculate the parts per million. Similarly, if we will express this in terms of volume, then we will write volume of one component upon the total volume of the solution into 10 to the power 6. So this ppm is used to express the concentration of such solutions which are very dilute. I hope you have understood. Next is which concentration terms are temperature independent. This is very important. See, we are having various concentration terms. Just we are having the molarity, right? We are having the normality, right? We are having the formality. So these concentration terms, they are temperature dependent. They are temperature dependent. They will depend on temperature because they actually involve the volume. This is very important. They involve volume. But if we just look on molality, that is small m. Similarly, if we have the mole fraction, right, mole fraction, which is represented by this symbol chi, mole fraction. So we are having molality, mole fraction. Similarly, the mass fraction. So they are your temperature independent because they involve the mass. They don't involve any volume, so they involve mass of the solvent or mass of the solution. So that is why they are temperature independent. So this will be very important. Molality, you will remember, mole fraction and mass fraction, they are temperature independent. Then we are having the next question, that which concentration term is regarded as better for expressing its concentration? See, you will remember that those concentration terms which are temperature independent, they are better concentration terms. For example, a question will be asked, is molality better concentration term or molarity? So you will remember that molality is better concentration term as compared to molarity, because molality is temperature independent, so it will not change with change in temperature. So that's why this molality, it is regarded as better concentration term than molarity. So I hope you have got this. Next, let's move to the next question. So next we are having question number 4, that is which is more concentrated, 1 molar solution or 1 molar solution? So that means if you are having 1 molar solution and similarly 1 molar solution, so which is more concentrated? So definitely we know that what is 1 molar solution. It is simply when we are having 1 mole of solute and it is dissolved in 1 liter of solution, right? 1 liter of solution. But what is molality? Molality means when we are having 1 mole of solute, right, and it is dissolved in 1 kg of solvent, 1 kg of solvent, right? Here it is 1 liter of solution, right? So you can now easily understand that this 1 molar, it is more concentrated as compared to 1 molar solution, because here in both the cases we are having 1 mole of solute, but here we have dissolved it in 1 liter of solution, right? But here we have dissolved it in pure solvent, that is 1 kg of solvent, right? So this 1 molar solution, it will be more concentrated as compared to 1 molar solution. Next is what is the unit of mole fraction and mass fraction? See, whenever we are expressing mole fraction, so what is mole fraction? It is simply the number of moles of one components upon the total number of moles of all the components, right? So it will not have any unit, so they are unitless. So you will remember that this mole fraction and mass fraction, they will be your unitless quantities. But other concentration terms, just we are having the molarity, so it has unit, that is moles per liter. Its unit is moles per liter. Similarly, if we are having normality, the unit will be the gram equivalents, right? You'll write it as gram equivalents, gram equivalents per liter. Or sometimes you can also express it as equivalent per liter. Similarly, if you are having molality, then it will be moles per kg. Moles per kg, it will be the unit of molality, isn't it? So similarly, if you are having let's say, if unit is given to you, let's say for example, if it is gram per liter, so this is the unit of strength, another concentration term that's called the strength. So strength of solution, it is expressed as gram per liter, isn't it? But you will remember that this mole fraction and mass fraction, they are your unitless as well as dimensionless, isn't it? So next is question number 6. This is what happens to the solubility of a solid in liquid solution if the dissolution process is exothermic. So you have to remember that whenever you are having any exothermic process, then if you will just increase the temperature, the solubility will decrease, just opposite. But if you are having any endothermic process, endothermic, if the dissolution is endothermic, for example, if you just dissolve sodium chloride in water, that process is endothermic. At that time, if you will just increase the temperature, then solubility will also increase, but if dissolution of solute or dissolution of solid, it is exothermic. For example, if you are having lithium carbonate, right, if you will just dissolve it in water, the process is exothermic. At that time, if you will increase the temperature, the solubility will decrease. So you have to remember that the solubility of solid in liquid solution, it will just decrease if the dissolution process is exothermic, right? So you will remember this. Next is very important here. Actually, we are having 3 types of salt. So one type of salt is that when we dissolve, the process will be exothermic. As I told, just we are having cerium sulfate, just we are having lithium carbonate. But we are also having those salts which when we dissolve in water, the process is endothermic. So that means heat energy is absorbed. At that time, if we increase the temperature, solubility will also increase. But there is one exception, and I hope you will remember that. That is known as Glober's salt. I hope you have gone through this. Glober's salt, it is actually sodium sulfate decahydrate, 10 times water of crystallization. So this is a special salt. Here what happens, first of all, if you just increase the temperature, the solubility will also increase up to 32.4 degrees Celsius. But after that, if you will increase the temperature, the solubility will decrease. So you have to remember that it shows peculiar behavior, we can say, that this Glober's salt, its solubility increases on increasing temperature up to 32.4 degrees Celsius. But after that, if we will further increase the temperature, then its solubility will decrease. So this is one of the salt which actually shows unique nature or the behavior which you will remember here. So this is Glober's salt. Next is dissolution of gas in liquid exothermic or endothermic? So the answer of this is, it is always exothermic. So dissolution of gas in liquid is not endothermic. You will remember it. It is always exothermic. It is always exothermic. So this is your question number 7. Let's move to the next question number 8. So question number 8 is given that what happens to the vapor pressure of a solvent if a non-volatile solute is added to it? So it is very simple, that if you just add a non-volatile solute to a volatile solvent, its vapor pressure will definitely decrease. Vapor pressure decreases. So vapor pressure will decrease when a non-volatile solute is added to a volatile solvent, right? So next is what happens to the solubility of solute in solution showing positive and negative deviation, right? So we have to actually discuss here uh, two different types of deviations. One is the positive and negative deviation. So let's have a look in detail. For example, if you are having any solution which is violating the Rolle's law, right, that's your non-ideal solution. So non-ideal solutions are of two types. One is that solution which shows positive deviation, another is that which shows negative deviation. So positive deviation is actually that when you just add a solute to a solvent, and in the solution what happens, the AB interactions, that is the interaction between solvent and the solute, AB interactions, they are weaker than they are weaker than solvent solvent interaction, that is A interaction, and solute solute interaction, that is BB interaction. So at that time we get a positive deviation solution. That means a solution which shows the positive deviation. When you have to remember that when AB interactions they are weaker than AA and BB interactions, at that time we get positive solution. That means solution which shows positive deviation. And similarly it's opposite, that is if AB interactions are stronger than AA and BB interaction, then that solution will be your that one which shows negative deviation from Rolle's law. Now what will happen to the solubility of solute? See, in case of if we are having a positive deviation solution, if we just see its solubility will increase. The solubility will increase in case of solution which shows positive deviation, but in case of negative solution the solubility will decrease. So you have to remember that if we are having positive deviation, a solution which shows positive deviation, it is solubility increases. Its solubility increases with rise in temperature. With rise in temperature, solubility increases with increase in temperature, right? And in case of solution which shows negative deviation from Rolle's law, you have to remember that the solubility decreases with increase in temperature. With increase in temperature, right? So actually here you will remember the all differences between the solutions which show positive and negative deviation. As you know that in case of ideal solution we are having del H mix, right? That is the enthalpy change after mixing. In case of ideal solution it is zero, right? Similarly in case of non-ideal solution it will not be equal to zero. Similarly, if we are having del V mixing, right, that is the change in volume after mixing, it is zero in case of ideal solution, but in case of non-ideal solution it will not be equal to zero. So when we are having a positive deviation solution, that means a solution which shows positive deviation, at that time del H mixing it will be greater than zero. Similarly del V mixing it will be greater than zero, isn't it? Similarly you will remember that the total vapor pressure of the solution, that is total vapor pressure of solution, partial pressure, it will be greater than PA plus PB, that is the partial pressure of both the components. So it's in case of positive deviation, right? In case of negative deviation it will be less than PA plus PB. I hope you have already gone through this and you will remember all the points of differences between ideal and non-ideal solutions. Similarly non-ideal solution showing positive and negative deviation. Then next is what are azeotropes? Azeotropic mixture, it is actually constant boiling mixture. So if we are having constant boiling miscible mixture, so that's your azeotrope. And how are they separated? You will remember that they are not separated by fractional distillation. There's a special technique that is called the azeotropic distillation. So with the help of azeotropic distillation we can separate this azeotropic mixture, otherwise it is not possible with fractional distillation. इसको याद रखेंगे आप. Next जो है that is colligative properties, they depend on, this is very important, you already have studied that colligative properties, they depend on number of solute particles, right? They depend on number of solute particles. That means we can say that they depend on the molar concentration, or you can simply say that these colligative properties they depend on number of moles of solute. So either you can say number of solute particles, or they depend on molar concentration, or you can say number of moles of solute, right? Number of moles of solute. This will be important. So then let's see the next one. Next you are having, that's question number 12. What will happen to freezing and boiling point of liquid if a non-volatile solute is added to it? If a non-volatile, here it's solute, if a non-volatile solute is added to it, right? So you will remember that, see, when a non-volatile solute is added, right, to a liquid, what will happen to its vapor pressure? Vapor pressure decreases. As we have already discussed it, that when a non-volatile solute is added, vapor pressure decreases. So what will happen to it is boiling point and freezing point. Boiling point, you will remember that boiling point, it will increase. What we just, as we have studied, one of the colligative property, that is the elevation in boiling point, right? It is the same. So similarly, what will happen to the freezing point? Freezing point, it will decrease. Depression in freezing point, right? Depression in freezing point. So you will remember that we are having the four well-known colligative properties, right? One is the relative lowering of vapor pressure, another is the elevation in boiling point, another is the depression in freezing point, another is the osmotic pressure. So here you will remember that boiling point, melting point, and lowering in vapor pressure, they are not colligative properties. Relative lowering in vapor pressure is a colligative property, but lowering in vapor pressure, that's not a colligative property. Similarly, elevation in boiling point is a colligative property, but boiling point itself, it is not a colligative property, right? So what you have remember now, what will happen to freezing and boiling point? So freezing point, it will decrease, and boiling point, it will increase. Next is, which colligative property is used to measure the molar mass of proteins and polymers? So definitely it is the osmotic pressure. Osmotic pressure is usually used to measure the molar mass or the molecular mass of proteins and polymers. So all these polymers, isn't it? You will remember also here that this osmotic pressure, it is actually measured by Berkeley and Hartley's method, right? I hope you have gone through that. That is very important for exam. You will remember that diagram too. Similarly, for we are having a relative lowering of vapor pressure. Which method is used? That is Ostwald's and dilution method, right? Ostwald's and Walker method. You'll remember that. So the next question is that, if two solutions are isotonic, what will be their molar concentration? What will be their molar concentration? So you will remember that if two solutions are isotonic, isotonic means having same concentration. Iso means same. So isotonic solutions, they will definitely have same molar concentration. So the answer will be, they will have same molar concentration. Now the question for you is that, what will be their osmotic pressure? So you will remember that isotonic solutions, they have also same osmotic pressure, which is represented by pi, right? Osmotic pressure भी उनका same होगा और molar concentration भी same होगी. So if two solutions are isotonic, they will have same osmotic pressure, they will have same molar concentration. And here it's very important that 0.9% NaCl solution, it is isotonic with RBCs, red blood cells, right? Blood cell, and 0.9% NaCl solution, that's isotonic. That's why it's used in injections. And next question is that, if a solute dissociates in solution, then what will be its Wat-Hoff factor, right? See, you will remember that if a solute is dissolved in a solvent, then neither it associates nor it dissociates, then Wat-Hoff factor will be equal to 1. It is for those solutes which neither undergo dissociation nor undergo association. But here the question is that solute dissociates. At that time, you will remember that the value of Wat-Hoff factor, it will be greater than 1. It's for those which will undergo dissociation. And similarly, if it is less than 1, at that time, that means you have to understood that solute have undergone association. So when there is association, just if we are having acetic acid molecules, they due to hydrogen bonding, they undergo association. So at that time, the Wat-Hoff factor, it will be less than 1. So I hope you have understood this. Then let's move to the next question. That is question number 16. That's what happens to the solubility of a solution if kh value increases. Kh is Henry's constant. So first of all, you will remember here that if kh value increases, you will remember that if temperature increases, the kh value will also increase. So by increasing temperature, the Henry's constant will also increase. Now if Henry's constant value increases, the solubility will decrease. So you will remember that the solubility of a solution, it will decrease if kh value increases. For example, if I am having the hydrogen, nitrogen and helium, among these helium has very high Henry's constant value, so that's why its solubility will be very less. So that means you have to remember that higher the kh value, lesser will be the solubility. But if kh value is small, then solubility will be very high. Just this hydrogen, it's having high solubility as compared to these two, because nitrogen and helium, they have high kh value. That is the Henry's constant. This is very important, Henry's law. I hope you have gone through this and you will revise it. Next is, under what conditions Henry's law is not applicable. That means you have to simply tell what are the limitations of this Henry's law, where it cannot be applied. So three cases are where it can. First of all, it is not applied if solution is non-ideal. So it should not be non-ideal, it should be ideal. That means Henry's law, it is applicable for ideal solution. So if we are having non-ideal solution, it is not applicable. Similarly, next is that if we are having let's say we are having a gas, right? And this gas, it either undergoes dissociation or it undergoes association when it's put in solvent. So at that time Henry's law cannot be applied. Next is that if we are having any gas and it reacts with solvent, if it reacts with solvent, at that time we cannot apply Henry's law. For example, if it's my nitrogen ammonia gas, let's see, I am putting it in solvent hydrochloric acid, at that time it will just react it with. So at that time Henry's law will not be applicable. So you will remember these three cases where Henry's law cannot be applied. Next is a mixture of hexane and n-hexane and n-heptane. They are examples of definitely the ideal solution. So ideal solution is that in which AA interaction, right, and similarly BB interaction, it will be equal to AB interactions. So it is only possible if we are having a similar type of solute and solvent. This is n-hexane, non-polar, and n-heptane, this is also non-polar, both are straight chain. So definitely they will form ideal solution. And for ideal solutions, I have already told that del H mixing, that will be equal to 0. Similarly, del V mixing, it will be equal to 0, isn't it? And similarly, the total vapor pressure, it will be equal to the sum of the partial pressure of the components, right, A and B, let's say. So this will be your ideal solution. And in case of non-ideal solution, these interactions are not equal. Similarly, delta H will not be equal to 0, delta V will not be equal to 0. Similarly, total vapor pressure of solution, it will not be equal to PA plus PB. You have to remember this, isn't it? For example, if I just talk of let's say now we are having non-ideal solution, which shows positive deviation. So in case of positive deviation, how you will differentiate it? This question will be asked. This is very important. For example, if you are having just ethanol, alcohol you are having, right? Let me write alcohol, ROH, right? So alcohol molecules, they are just bonded with each other due to hydrogen bonding, right? Now if I am just putting acetone in it, in this alcohol I am putting acetone, so acetone will break these hydrogen bonds, right? At that time we will get solution which will show positive deviation from Rolle's law. Similarly, if we are having now let's say chloroform, so chloroform is just like this, that is CHCl3, isn't it? So if I'm just putting it in acetone, so acetone I can show like this, C double bond O. So here we are having CH3 and here also another CH3. So what will happen when we will put this chloroform in this acetone? There will be now hydrogen bonding between this hydrogen and oxygen. There will be hydrogen bonding, and due to this hydrogen bonding, the total volume will decrease. That means it will be now such solution which will show negative deviation from Rolle's law. This is very important. I hope you will remember the examples of solutions showing positive deviation and showing negative deviation. Particularly this example, it is given in your NCERT textbook. You will remember this, that if you are having ethanol and acetone, that is example of a non-ideal solution showing positive deviation. And if you are having chloroform, that is CHCl3 and acetone, that will form non-ideal solution which will show negative deviation, right? So next is, which process is used for desalination of seawater? It is actually desalination, DE. That's actually the reverse osmosis. So reverse osmosis is used for desalination of seawater. This very important application of this reverse osmosis. Reverse osmosis, when it is possible, this is very important. It is possible when the external pressure, it is greater than the osmotic pressure. At that time there will be reverse. In case of reverse osmosis, what will happen? Water will move from higher concentrated solution to lower concentrated, right? This is very important. So this was question number 19. Let's move to the next one. Next is here you are question 20. 20 is that which aqueous solution will have the highest boiling point? See, actually here you, various solutions will be given to you just like this. 0.1 molar NaCl, let's say we are having. Similarly 0.1 molar, let's say sodium sulfate you are having, right? Similarly 0.1 molar urea you are having, right? Similarly, let's say 0.1 molar potassium nitrate you are having. So among these four, you have to tell which will have highest boiling point. So we have already studied the colligative property. So colligative property, you know, it depends upon the number of solute particles, that is the number of moles. So when it will dissociate in water, NaCl, it will give 2 ions, right? Sodium sulfate, it will give you 3 ions, right? Urea, it will not dissociate at all, and this will give you 2 ions. So where is the maximum number of particles? That is here in case of sodium sulfate. So this will be the correct option for this. So you will remember that 0.1 molar sodium sulfate will be here the answer. That means it will have highest boiling point, correct? So that means simply when these this type of question will be asked, you have to remember that that will be the correct option. That electrolyte, that salt, which will give maximum number of ions. For example, this NaCl, it gives only 2. Potassium nitrate, it gives 2. Urea, it will not dissociate because it's not salt, it's not ionic compound, but this will give 3 ions. So more the number of solute particles, more the number of moles, right? Then more will be the colligative property value. So that means here highest boiling point will be that of sodium sulfate. Next is that intermolecular forces between two benzene molecules are nearly of same strength as those between two toluene molecules. Then the question is that for a mixture of benzene and toluene, which of the following are not true? So you have to remember that here question is given that which is not true. First of all, you will see here we are having benzene and toluene. So benzene and toluene, both are what? Both are your non-polar and they will resemble with each other. This is the benzene and this is your toluene, that is the methyl benzene. So this is actually example of ideal solution. So tell me, in case of ideal solution, which is true? So del H mix, it is del H mixing, it is 0, so it is true. You have to tell which is not true. Del V mixing, it's also 0, it is true. So there will these will form minimum boiling azeotrope. No, not at all. Azeotrope, minimum boiling and maximum boiling, that is actually formed by non-ideal solutions showing positive and negative deviation. So this will be the correct option for this question. Next we will see these will not form ideal solution. They will actually they will form ideal solution because I already told they will form ideal solution. So you have to tell which is not true. That is this one, option C, this one, because here you will remember that those non-ideal solutions which show positive deviation solutions, they form minimum boiling azeotrope, right? And those non-ideal solutions which show negative deviation, they will form maximum boiling azeotrope. They form maximum boiling azeotrope, right? So here this is example of ideal solution, so it will not form any azeotrope. You will remember this very important, positive and negative deviation solutions which will form what type of azeotrope. So minimum boiling azeotrope, it is formed by such solutions which show positive deviation, and maximum boiling azeotrope, it is formed by such solutions which show negative deviation. Next is out of 1 molar urea solution and 1 molar KCl solution, which has higher freezing point. So you have to tell here that which has higher freezing point. This is very important. It is not here now the boiling point, it is the freezing point. So its answer will be 1 molar urea, because it will not ionize at all. KCl will ionize, it will give two ions, one is K positive, another C negative, Cl negative, right, chloride ion. But here urea, it has lesser number of moles, so it will have higher freezing point. But the important thing is that if question is asked that out of 1 molar urea solution and 1 molar KCl solution, which will has higher depression in freezing point. If question is asked that which will have highest depression in freezing point, then you will remember that the answer will be KCl at that time, because it has maximum number of ions it will give in the solution. So number of moles will be more, colligative property will also be more, and this we already know that depression in freezing point, that is a colligative property, but freezing point, it is not a colligative property, right? Yeah, you will remember it here, that if question will be asked that which will have highest depression in freezing point, then the answer will be KCl, but here the answer will be 1 molar urea, because here it has been asked which has higher freezing point, right? So its answer will be 1 molar urea. So I hope that you have understood each and everything. Still, if you have any doubt, you can just comment in the comment section below, and also you can join the Telegram channel and the WhatsApp channel, from where you will get the latest updates. And wish you all the very best. See you in the next video. Thank you.